Okay, so good afternoon and welcome to the Genetically Modified Salmon panel. You've heard of GMO produce, but for the first time in history, the FDA has approved the genetically modified salmon as the first living organism to be approved. I'll be your moderator today. I was chosen because of my experience in science and law, but I was also speaker chair last year, so I was an easy target when they were looking for recruiters. So our speakers today are Mr. Ricardo Carvajal. He is an experienced FDA lawyer at a DC-based firm, and he has previously worked for the FDA. Our next speaker will be Dr. Blum. He is a bioenvironmental scientist and a professor who specializes in ecosystem assessments and freshwater fish. Our last speaker will be Mr. Tim Schwab, and he works for the Food and Water Watch. It's a nonprofit organization, and he has been following the GMO salmon FDA approval process since 2010. So please have a seat and join me in welcoming today the panel.
Good afternoon. My name is Michael Blum. I'm a professor here at Tulane in the Department of Ecology and Evolutionary Biology. I'd like to thank the organizers first for inviting me to participate on this panel. So I'd say that fish, not necessarily salmon per se, but fish are near and dear to my heart. So I've spent a career looking at fish. I was actually a card-carrying salmonid fisheries biologist prior to going back to graduate school. I worked on a Chinook fishery in the Central Valley of California, and it gave me a real immediate understanding of what life was like as a salmon and what life is like in the world of salmonid fisheries management. So today I'm going to do three things. If I can work this computer. Okay, so I'm going to give you primers on three topics. One is on the rise of farmed Atlantic salmon. So why are we even talking about GMO salmon and Atlantic salmon in particular? Why is it important? I'm going to talk about the biology, the mechanics behind how we make fish bigger. So is GMO salmon the only option in front of us, or are there other ways in which we can pursue the development of a broader fish production stream? And then the last thing I'm going to do, because I'm a biologist, I'm going to focus on some of the environmental risk concerns, particularly issues of accidental release and gene escape. And I suspect that these topics will come up in the other two talks that you'll hear from the panel today. But this is going to be, again, just a primer of what I think of as being sort of foundation of the discussions that contextualize Atlantic salmon. So again, why are we even talking about Atlantic salmon? So a good place to start is to look at worldwide fish consumption trends. So no surprise, fish consumption trends are increasing over time. If you look over the last 50 years or so, we're looking at a five-fold increase, arguably even a larger increase in fish consumption. So there's this question of whether fisheries production can keep pace with fish consumption. So there's a very large market demand for fish protein, and in particular wild-caught fish protein. And what has been argued recently is that worldwide fish production, particularly wild-caught fish production, is arguably at a peak state. So some of you have probably heard the term peak fish, like peak oil, but the expectation is that wild-caught fisheries are at a peak and that over the future they will decline in productivity over time. This is a nice portrayal of salmonid fisheries. So again, these are wild-caught fisheries. And you can see over, again, about a 50-year period, we've seen a very large increase in fisheries productivity. Looking at the y-axis, though, this is, again, a very small fraction, maybe 1% of overall market demand. So salmonids are a very important component of fisheries, but they're a relatively small component of fisheries from a global perspective. So if we look at this question again, we understand that consumption and demand is rising. We're at peak fish, or perhaps at a steady state in fisheries productivity. How do we fill the gap? What do we do to meet the demand? So what we've seen over time is that aquaculture production has increased tremendously over the last 50 some odd years to fill that gap. And the expectation going forward is that aquaculture, in particular fish aquaculture, will continue to rise. So there's some expectation that wild-caught fisheries may, again, stay at a steady state, arguably possibly decline a little bit, but there's no question that aquaculture is going to increase going into the future. If you break down aquaculture and you look at the different components, which components are really driving the increase? So we certainly see an increase in things like mollusks, shellfish, but we can point out that fish, finfish, is, again, a large component of aquaculture, and the expectation is that it will become increasingly larger over time. If you break out finfish and you look at the different components of finfish, what are the largest constituents in the fisheries world? Freshwater fish arguably is the largest. So think about things that you might or might not like to eat, like carp. Carp isn't something that we eat in the United States, but it is a very large aquaculture fishery in East Asia. Focusing again on diagamous fishes, so salmonids are diagamous. It's a particular kind of life history that involves a marine stage and a freshwater stage. Diagamous fishes are a relatively small component of aquaculture to date, but again, it's a fairly important one when we look at consumption trends. Looking at consumption trends. So I think this is notable. Why aquaculture, again, is important not just for the purposes of feeding people. When you look at the peripheries, I think it's notable to indicate some of the benefits that are derived from aquaculture. We certainly can point to the detriments, and I'll speak to that in a moment, but one of the benefits about aquaculture links back to carbon footprint. So we can say, again, from a very basic comparison, how much carbon is introduced into the environment with farmed fish versus, say, beef production. There's a much, much smaller carbon footprint for farmed fish or aquaculture than there is for beef production. No real surprise there. The most important thing that is illustrated on this trend is that beef production is holding steady and farmed fish is increasing and is arguably going to overtake beef as an important source of protein worldwide very, very soon, if it hasn't already. So breaking it down even further. So we're here to talk about salmon. Let's look at salmon in detail. We look at diagamous fish production. Most recent statistics suggest that, again, farmed salmon is increasing tremendously over time, whereas wild-caught fisheries are more or less holding steady. If you break out which species are most important, in parts of the the farmed salmon fisheries, we see that Atlantic salmon falls out very, very clearly as being one of the largest parts of that production line. Where is this happening? So this is worldwide, both hemispheres. We're looking at this in Chile, we're looking at this in Norway, Canada, United States. So this is something that translates across international borders. And as the numbers break down, Norway comes out as being the largest producing nation. Canada, again, is very important. Chile is very important. These play into where some of the concerns lie with aquaculture and potential environmental risks. So what's the geography of that risk? I also like to put up this number that this is a monumental fishery. So we look at this relative to other things that we're familiar with. So how does this compare to, say, like the NFL? Is this comparable or smaller? Does everybody watch the Super Bowl? Yes? No? Maybe? I did. It was fun. This is comparable to the NFL. So the NFL has roughly a $10 billion annual revenue stream. This is about that same size. So this has large-scale penetration and scope as an industry. Looking at how this grows. So we understand that aquaculture is going to grow over time. So what are some of the concerns? These are things which I'm not going to go into a lot of detail today. Certainly when we look at pens or farmed aquaculture facilities like this, nutrient loading is certainly of concern. Disease or pathogen transmission is certainly of concern. Growth, physiological, individual level growth is certainly of concern. It's a limitation. So if you're a farmer, whether you're talking about corn or you're talking about soybeans or salmon, you want to improve productivity, and one way of doing that is improving the growth or the size of the organism in which you're working with. So how do you make a bigger fish? Okay, so again, we're talking about GMO and genetic engineering as being at the forefront of this question. But this is a question that arguably goes back into prehistory. Folks have worked with fish for centuries, if not millennia. And if you look at the culture, let's say the historical culture behind working with fish, It's to no surprise that this is very similar to other elements of agriculture. So we understand that artificial selection is very much part and parcel with aquaculture. So this is something which, whether you're working with salmon, you're working with tilapia, you can individually select for desired traits. And what's important here is that this is based on natural heritable variation. Okay, this is genetic variation that is implicit or intrinsic in the organism in which you were working with. Okay, so some of the concerns about this, some of the limitations, why it's not enough. I should say that this is actually proven to be highly effective in improving growth. So if you look at wild-caught fish versus selected farmed fish, you're looking at a 200% increase in growth just based on artificial selection. So again, some of the concerns, why people are looking at alternatives to artificial selection, it takes a long time. So not only do you need a lot of standing variation, you also need many generations to effectively express that variation across your populations of interest. There are trade-offs. Okay, so this is, again, to no surprise, when you're selecting for a particular trait, there are other traits that may come up that are undesirable. For example, disease. So other things to be concerned about. In terms, again, if you're a farmer, there are limitations. There's only so much that you can do through artificial selection. So there are certainly some intrinsic limitations. For example, again, the standing heritable variation that you have in your populations. And then there are limitations imposed by the environment. So that's referred to as genetic by environment interactions, where effectively, whether it's the interaction or the environment by itself, it limits the growth potential of the organism. Other option. So I suspect that most of you are not familiar with the induction of triploidy as a potential avenue for improving growth. This isn't something that is often talked about, but it's part of the production stream actually in the GMO production cycle. It's early on, and I'll note this in a moment. Very, very briefly, not to go into the details of this, but effectively it's what's referred to as chromosomal retention. And through chromosomal retention, by way of imposing pressure during early development, you get a triploid organism from a diploid background. That triploid state leads to sterility. So the expectation is that triploid organisms are not capable of breeding. That's not 100% true. There are triploid organisms that can interbreed. There are statistics that suggest that we're looking at 90 to 99% sterility, particularly in females. Males are expected to have a little bit more capacity to reproduce. Why do we see an increase in growth? It's a very simple physiological trade-off. So those organisms which cannot reproduce put that energy and put that let's say, activity into growth. So those things that don't reproduce put that, again, activity or energy into growth. So it takes time for the growth to unfold. So it's not something that you see immediately. It's something that you see over the course of a life cycle. And again, why you don't hear about this very often is because it's intensive and it has technological limitations on production. Genetic engineering. Okay, so how does genetic engineering differ from, say, artificial selection? So a very important distinction is that it involves the introduction of a novel genetic element for the expression of a desired trait, whether it's growth or something else. You're taking a genetic element that is extrinsic to an individual genome. In the condition of transgenesis, you're talking about taking a genetic element from one species and putting it into a second. And we have genetically modified organisms that have genetic elements that are derived from many, many different species. In fact, we'll talk about, again, the GMO salmon, where we have genetic elements from two very distinct species being put into a third. What are some of the concerns with this? Of course, it's technologically very complicated, very similar in many respects to the induction of triploidy, so the production lines aren't quite the same as, say, artificial selection. There are recognized environmental risks with this. So before I was a faculty at Tulane, I was a research scientist at the EPA, and for about a 2-year period, I worked on their GMO task force, focusing on some of the research questions associated with environmental risks. Two of which I focused on. One is non-target concerns, and the other is genetic escape or hybridization. And the last thing, and I won't, again, focus on this isn't my area of expertise, but there are concerns in terms of public health and the ethics behind GMO organisms, and I hope that the other panelists will tell you a little bit more about that. Again, what we're talking about today, GMO salmon, just to give you a very quick overview of what this involves from a biological perspective. So we're talking about a very specific product called Aqua Advantage salmon, AA. It's great for like a Yellow Pages listing from Aqua Bounty Technology. We're talking about two steps, actually. The induction of triploidy, which is intended to introduce sterility into the production line, and then transgenic modification, again, of Atlantic salmon with a gene that codes for growth hormone from Chinook salmon that's tacked to a promoter region, which effectively controls the expression of growth hormone. And so the important part of this is that Atlantic salmon, under natural conditions, are limited in their growth seasonally, so they don't grow during very cold conditions. Not surprising. Very few organisms do that. But the thing that was effectively, I won't say exploited, but ocean pout is capable of winter growth because it has what's referred to as antifreeze in its bloodstream. So it has some tolerance to cold. And so by way of taking that element and tacking it on to a growth hormone expression area, it introduces the capacity for year-round or annual growth. So what does that end up translating to in terms of production? Very simply, it allows the salmon to grow more quickly to market size. So in about 50% of the time. So rather than 3 years, it takes about a year and a half for it to meet market demand. So some of the interesting elements of this in terms of the background, where you see the expression of growth differences most is under hatchery conditions. So the expectation is that production will be done under hatchery conditions, and it makes sense just looking at the picture, that's where you get the biggest product. If these things hypothetically were to be released, would these fish still have a competitive advantage due to year-round growth? So they would still sustain a difference, but it would be arguably much less so than under hatchery conditions. Other things in terms of why there's some advantage to the aquaculture advantage, salmon. Again, sort of the peripheries of this and really understanding actually the core of the production cycle. This gets down to cost. So salmon, like any other agricultural product, costs money to produce. And this particular technology reduces costs by about 25%. So whether we talk about it in terms of the translation of feedstock to protein, or whether we talk about it from cost, this is a real advantage in terms of producing farmed salmon. Why are we concerned about this? Okay, so undoubtedly you have all heard of GMO crops or organisms, whether it's plants or animals. You have some idea of the concerns that come with them. As a biologist and as an ecologist working on invasive species over the last few years, particularly, this is what I focus on. Okay, so the potential for what's referred to as accidental release. Okay, so you're farming salmon, whether it's offshore or whether it's in inland pens, and it gets out. Okay, so what happens to that? We understand, again, looking at this globally, that this is not an unusual phenomenon. Okay, accidental release happens all the time. Okay, so we can look at some very gross numbers here. About 40% of aquatic invasive species are from aquaculture facilities or aquaculture production. 40% worldwide. How do you get a fish that originates from South America into Africa? How does a fish coming from Africa get to North America? By trade, by aquaculture. Okay, again, we see this broadly. Particular to fish, we understand that 50% of aquacultured fish have been released into the environment. 50%. It's a big number. To illustrate this a little bit more, I suspect that you have all heard of Asian carp. Okay, for those of you who are from the Midwest, watch out. Literally, watch out. Other things that you may have heard about, tilapia. So tilapia is a fin fish that's broadly produced across the world. It's been broadly released across the world. Chinook salmon, again, within the salmonid family, it's broadly produced across the world. It has been extensively released, particularly in South America. So accidental releases is not a hypothetical. It's a reality. It's something that everybody deals with in my world. What about Atlantic salmon? Okay, so these are farmed Atlantic salmon. These are things that have been selected for. So these are not GMO salmon. These are, again, artificially selected farm lines. Does accidental release happen? Yes, it happens extensively. So we can look at the west coast of North America, where Atlantic salmon are not native, and we can ask this question very simply. Where you have Atlantic salmon farming, do you see Atlantic salmon in adjacent rivers? And I would say that the map tells the story very clearly. You see them extensively, and they're proximate to farming operations. And why are we concerned about accidental release? Certainly we want people to be accountable for the release of their organisms under production. But the things which I am concerned about, again, as an evolutionary biologist and as an ecologist, we understand that there are very specific outcomes. Competition between introduced fish and native species, particularly threatened and endangered species, including native salmonids. Disease, pathogen transmission is certainly of concern. Predation, again. When you have a top predator, what happens when it gets into the waterways? It eats everything smaller than that. Hybridization. So my particular expertise is on hybridization. We understand that salmon and fish have a tendency to hybridize more so than any other vertebrate on Earth. So whether you're talking about mammals or whether you're talking about birds, fish have a propensity to hybridize. Sorry, let me go through this very, very briefly because I know my time is limited. Studies that have been done to just look at the relationship between wild-caught fisheries, so again, natural wild-caught fisheries, salmon, and this is a mix of Atlantic salmon on the top two rows, and then this last graph here, and then a few conjugates of other salmon on the Pacific coast. Very simple question again is, where you have farm operations, what do you see in terms of the adjacent or nearby wild-caught populations, or things that are a control situation? We see a predominance of evidence suggesting that where farming increases, wild-caught fisheries decline. So, gene escape. This is evidence from plants. Does it happen? The answer is yes, it happens. So we have yet to approach the concern with GMO salmon. It's not in a situation yet where this is a concern, but if you look at plants, again, looking at precedent, we understand that gene escape happens, and it happens extensively. So you can look across broad landscapes, like North Dakota, the entire state of North Dakota. There are transgenic canola plants found all across North Dakota, and not only things that were originally designed, but things that are novel. Safeguards. So this is the last part of the story. What can we expect from GMO salmon? This is what I'd like to leave you with. Right now, there are two safeguards that are in place. One is, again, the induction of triploidy, which reduces the potential for them to reproduce under natural conditions. It is not foolproof, nor will it ever be. And secondarily, it's land-based production outside the United States. We'll put that outside of the United States as, say, a special condition. It's irrelevant in many respects if you look at things from a global perspective. But these are two important safeguards at this point that reduce the possibility of things like gene release from happening. The future of aquaculture. GMO salmon certainly is on the forefront of everybody's minds for good reason. It's the thing that's farthest forward in the production cycle. There are other things that are to follow. And hopefully, again, my colleagues on this panel will tell you a little bit more about that production cycle and where things are going. Thank you.
This small room, everybody can hear me with or without the mic, I hope. That's a hard act to follow. That was really good. I feel like I already got my money's worth. First off, thanks so much to the students who organized this. I don't know, you guys can be so proud of your colleagues because I go to speak at a number of conferences throughout the year. I have never seen something as well organized as this and been welcomed in the way that your colleagues have welcomed me. So I'm very grateful for it. So, quick show of hands, how many people are here for SailD? Hardly anyone, okay. How many of you are not a lawyer, not a law student? Really? Not a law student, not a lawyer. Okay, so this is a little tough because this is somewhat geared to the CLE crowd, okay, because we have to give them a CLE credit. But I'm not, so, okay, this is really good to know. I'm not going to spend a lot of time delving into the minutia of the law here. So, you know, the title says it all in terms of what you're about to hear. This product is being regulated under the Federal Food, Drug, Cosmetic Act. That's the same law under which the Food and Drug Administration regulates a lot of the things you eat, your medicines, your medical devices, the tobacco you smoke. 25 cents of every dollar flowing through the U.S. economy is regulated by FDA. Okay, so this is one more in a very wide portfolio of things that have run across FDA's desk. Is it right click or left click to advance? Right. Right click. Thank you.
Perhaps keyboard.
Oh, okay. Yeah, that would be easier. Okay. So, and just a very quick overview of this law. It's the law that I work with every day. I'm sort of one of those, maybe one of those not very common lawyers that is happy most of the time, in part because I'm working with this law, and it's a fascinating law. You know, 110 years now, starting with the 1906 Pure Food and Drug Law. There have been periodic amendments over the years. Every 10, 20, 30 years, there's another spasm, usually resulting from some kind of a public health issue that shows that there's some shortcoming or deficiency in the law, and we get an amendment, and then we all have to absorb that. But what you'll see over that course of 110 years is this balancing between, on the one hand, ensuring safety of these products that you all consume, and on the other hand, fostering innovation so that you can keep on getting additional products that tackle new problems and new challenges. And that pendulum, if you look historically, will swing back and forth. Sometimes FDA tightens up a little too much on safety, and then it gets accused of actually killing people. I mean, I've heard people say that, right? By keeping drugs from getting to market quickly enough. And other times they might loosen the reins a little too much, and then they get accused of killing people that way. So at least at FDA, the saying was, you know, if everybody's mad at you, you're probably doing your job right. You sort of found that sweet spot in the middle. It's a very broad, flexible statute, and I think this is a great example of why. So in law, definitions govern so much, and that is more true with the Food, Drug, Cosmetic Act than probably anything else I've ever worked with. There's a definition in the law of a food additive, okay, and it's up there for you. Any substance, the intended use of which can reasonably be expected to become a component of food. It's a very broad definition, and what's nice about it is that if anything falls under that definition, it's subject to pre-market approval, which gives FDA very tight control. But there's an exception, and that exception was put in by Congress. Again, as a result of that pendulum, we want to balance between safety and innovation. If the use of a substance in food is generally recognized as safe by experts in the field, okay, then it's not subject to pre-market approval. So everything that goes into the food that you eat, at least the non-animal food you eat, is either going to be a food additive that's been approved pre-market, or it falls out of that definition by virtue of being generally recognized as safe. And regardless of whether it's a food additive or grass, generally recognized as safe, the safety standard that applies is the highest safety standard that applies to any product that's regulated under the Federal Food, Drug, Cosmetic Act. And that standard is reasonable certainty of no harm. So let's start with food from GE plants, because I think it sets up a nice comparison once we start talking then about animals. Animal food, sorry, food from GE animals. The law was never specifically amended to address any of the challenges posed by genetically engineered plants, because FDA thought that it had a sufficient authority under the law as it existed. Remember, we talked about that breadth and that flexibility. And so their approach dates back to a 1992 Statement of Policy. Happy to give you the citation if you want to delve into that level of detail. And the core of it is that nucleic acids, so we were talking about the thing that's inserted, you know, the genetic material that's inserted from one species or another organism and put into a different species that has the intended effect, that's largely comprised of nucleic acids. And FDA looked at that and said, you know, nucleic acids are present in what we eat every day. There aren't any safety issues generally associated with those. So we're going to presume that they're grass, and therefore they don't have to be pre-market approved as food additives. The intended expression product is a different thing. So you're putting in the nucleic acid to achieve a particular effect that's achieved through the expression of some protein or peptide, and that might or might not be a food additive, depending on what it is. If it's something that's already present in the diet, and we're not raising the level that you're already consuming, then it's not going to be a food additive. It's going to be generally recognized and safe, and there won't be any pre-market approval. So that's been the framework now for going on 20 years, and FDA set up recognizing that there was still going to be a lot of controversy over these foods, they set up this voluntary pre-market consultation process, which reportedly every food that is genetically modified and currently on the market has gone through. So the company puts together a dossier that addresses safety, they submit it to FDA, FDA looks at it, and if FDA has any questions, there's a back and forth. If FDA doesn't have questions, they'll send the company a letter saying, we looked at your information and we don't have any questions. So why not regulate food from GE animals the same way? Okay? And it goes back to definitions. So if you go to a different definition in the Food, Drug, Cosmetic Act, there's a definition of drug that says that any article, in parentheses, other than food, so any article intended to affect the structure or function of man or animal is a drug. Now that parenthetical exception is there because obviously the foods you eat affect the structure and function of your body. That's one of the reasons you eat, right? So Congress didn't want to sweep in foods into the drug world. So they put in that parenthetical and they said anything other than a food, basically, that affects your structure or function is a drug. And on the animal side, we have human drugs, we have animal drugs. On the animal drug side, if it's not grass, and in this case it's grace because it's safety and effectiveness. We don't talk about effectiveness when we talk about foods. We talk about effectiveness when we talk about drugs. Okay? So if it's not generally recognized as safe and effective, then it is by definition a new animal drug and has to go through a pre-market approval process. So that's the regulatory box that genetically engineered animals fall into. They're not going to be regulated as food. They're going to be regulated as drugs. They're going to be, and so that's the most demanding regulatory paradigm. And because we're talking about a genetically engineered animal that's used for food, the safety standard is going to be reasonable certainty of no harm. So it's the most demanding safety standard. FDA lays all this out in a guidance that they issued in 2009, where they talk about the rDNA construct intended to affect the structure or function being a drug, and stating that submission and approval of a new animal drug application is required before you can get that on the market. The drug pathway is torture. So for human drugs, one of the reasons they're expensive is because it takes many, many years and many millions of dollars in investment to get them over the finish line. That's not really any less true on the animal drug side of the house. Here, this is sort of slanted more toward the animal drugs, the genetically engineered animal as an animal drug, but the elements are all the same elements that you'd see if you were trying to get a standard drug approved, something to treat an infection, for instance. All those same elements have been borrowed and modified by FDA into something that they think is appropriate to deal with the unique hazards and challenges posed by genetically engineered animals. So you have to have your product definition, what is it exactly that we're asking FDA to approve. You have to have a very detailed characterization of the construct so that FDA knows exactly what genetic material you're inserting and where you're inserting it. You have to characterize the lineage of the animal, so you have a progenitor organism and other organisms that are going to be descended from that. You have to characterize the type of animal that you're asking FDA to approve. You have to have a so-called durability plan, which is essentially intended to convince FDA that these genetic elements that you've inserted aren't going to start moving around or aren't going to change their expression over the life of the animal or downstream. Environmental and food and feed safety, which is what I'll focus on more. And then claim validation, which sounds a little weird. So, in the human drug space, if I tell you that my drug is intended to, pick whatever, let's stick with treat infection because that's a typical drug claim, or even a painkiller, reduce pain. I have to prove that the drug is effective. That doesn't really make that much sense in the context of the genetically engineered animal. In this case, the claim is what you heard my colleague talk about, that they grow out faster to maturity in less time. They reach maturity than their non-engineered counterparts. So all those things have to go into that new animal drug application. And that's what the product we're talking about today has been through. I didn't even talk about investigational new animal drug status. There's actually a step that comes before you submit a new animal drug application to FDA. But that actually happened back in 1995. The new animal drug application was approved in November of 2015. So we're talking 20 years and a little more than $80 million. Okay. And maybe that is part of the answer to the question you raised is, what about the other things coming down the pike? I think when they see figures like this, they wonder if they'll come down the pike. I wonder if they'll come down the pike here or in another jurisdiction that isn't going to set up these kinds of hurdles and roadblocks. So focus on safety. We talked about the standard that applies. Here it is in more detail. Reasonable certainty in the minds of competent scientists that the substance is not harmful under the conditions of intended use. And then here's the pendulum, right? Safety, but wait a second. Let's not go too far. It's impossible in the present state of scientific knowledge to establish with complete certainty the absolute harmlessness of any substance. That's Congress talking again. It's Congress talking through FDA, saying, FDA, don't go crazy on us here, okay? We want things to be safe, but water is toxic if you drink too much of it. Salt is toxic if you ingest too much of it. So we're not asking for absolute safety without any potential injury or any possible harm at all times. In terms of a little bit of the detail of FDA's safety finding, first, they looked at it and compared it to standard Atlantic salmon. They have an encyclopedia, believe it or not, of fish. And if you use the appropriate test method and you test Atlantic salmon, conventional Atlantic salmon, and you test the AAS, what that test result tells you is that AAS is an Atlantic salmon. They looked in excruciating detail at differences in food composition. So a wide variety of constituents that are normally present in food. Total protein, specific amino acids, vitamins, fatty acids, ratios of fatty acids, including the omega-3s and omega-6s, which you've probably heard about. We want to have lots of omega-3s in our diet. And they found no biologically relevant differences. There are no differences, right? No biologically relevant differences. Again, if you just focus on, are these things exactly the same? The answer is no, they're not exactly the same. But the extent to which you find differences, and they found differences, for example, in vitamin B6, they did very conservative assessments. They said, okay, let's say that this difference in vitamin B6, let's take the maximum difference we observed, and let's imagine that everybody eats nothing but this salmon, thereby exposing themselves to this additional level of vitamin B6. What does that translate into? In the context of what you eat every day, it doesn't translate into anything. And so here's the take-home conclusion from FDA. Food from AAS is as safe as food from non-GE Atlantic salmon. And there's a reasonable certainty of no harm from consumption of food from AAS. On the environmental side, the conclusion was no significant environmental impact, in part because of what you saw earlier. The product is produced in facilities in Canada and Panama. There are secure facilities. There are multiple and redundant forms of physical containment. I have diagrams and pictures of the facilities and the containment mechanisms if anybody wants to delve into that level of detail. By the way, I have a whole sheaf of stuff. If any aspect of this, for whatever reason, tickles your fancy and you want to know more, come see me because I have all the slide presentations that were used when FDA had an advisory committee meeting to get feedback on its approach to regulating this product. And so because of those forms of containment, FDA's conclusion was the possibility of escape and survival is, quote unquote, extremely remote, their words. So again, not zero, it's never going to be zero. That's about as strong a conclusion as you're going to see. And then because the animals are all female and sterile, as you saw, but again, not zero, possibility of reproduction in wild is extremely remote. So I guess you have sort of two implausibilities. One, you have a very low probability of escape and survival, and coupled to that, if you have escape and survival, you have very low probability of reproduction in the wild. Labeling is probably the one thing that gets people really fired up. Some of you might be in the pro-GMO labeling camp. Others of you might not care. FDA has very limited authority to compel labeling. For those of you who've done your constitutional law and you've learned about the First Amendment applies to commercial speech as well as other forms of speech. So FDA can't just go tell a company to put a statement on its product without any rationale. The rationale is in another definitional section of the Federal Food, Drug, Cosmetic Act, which says that a label is misleading if it fails to reveal, quote unquote, material facts. And to FDA, materiality means something very specific. That's a term and a concept they've been interpreting over the course of 40 years to mean something that is relevant from a public health standpoint. So if we're talking about drug labeling, an adverse effect, that's material. Okay? In the context of GMOs, once FDA has concluded that there's no safety issue and that there is no material difference in composition or nutritional value, there is no longer a hook for them to require labeling. In my view, there's an obvious and fair policy solution, non-GMO. The claim is out there, it can be certified, it can be verified, and I'm sure that if AAS gets to the market in the US, the conventional salmon producers will be rushing out to claim that their salmon is non-GMO salmon, and you will be able to choose freely. So beyond safety, socio-political views. Maybe you think GMOs are bad because it's corporate control of the food supply. Maybe you think they're bad because we're playing God. There are economic interests. Maybe you're an Alaska salmon fisherman and you see this cheap, abundant supply of salmon coming down the pike, and you ask your congressional representative to intervene on your behalf, as the congressional representative from Alaska has tried to do now for the last 5+ years running, more or less unsuccessfully up till now. And all of these things can be wrapped up into what I call the DC playbook, which is if you really want to stick it to a competitor, or you want to stick it to somebody who's trying to market something that you don't like to see on the market, there are lots of levers to be pulled in and out of government. I think it's sort of a fine line between, on the one hand, sort of legitimate opposition, and on the other hand, taking things to the point where you're sort of abusing the process and the transparency of the process. And I think 20 years is kind of pushing that limit. That's as close as I'll get to a soapbox. This is what we're talking about, right? Now, some people look at that and they say, ooh, Frankenfish, that's an abomination. I look at it, I see a pretty remarkable human achievement. And the first time I saw that picture, it reminded me of something that I saw for the first time at the Museum of Anthropology in Mexico City, which if you get to Mexico City and don't go to that museum, you are doing yourself a disservice. And this is the thing that I saw. Okay? So it took us 100 years, well, hundreds of years, to get from the thing that's on the left, the teosinte, which is the ancestor of the thing that's on the right. And that thing that's on the right, you eat all the time. You don't think it's unsafe. And I think eventually we'll get to that point with this. Okay? And if we don't, I think some other countries will. I just don't think this technology, the promise of this technology, if the risk can be managed properly, the promise is simply too much to reject out of hand. And I think the choice we face is whether we allow that technology to proceed here and reap whatever benefits can be reaped from it while we manage the risks, or we simply allow other jurisdictions to take that course. So that's all I am. Thanks.
How do I advance the slides? Yes, so I'm Tim Schwab. I work for Food and Water Watch. We're a nonprofit advocacy group based in D.C. Like many of you, I'm not a scientist and I'm not a lawyer, so I'm going to be bringing a different perspective. So the title of my presentation today is GMO Salmon, a risky solution in search of a problem. So this fish is very widely opposed. Consumers have said in many different independent polls from NPR, Thomson Reuters, New York Times, that they won't eat this fish and they want it labeled so they can avoid it. Leading grocery stores, not just the Whole Foods and the Trader Joe's, but the Kroger's, Target's, Meijer's, Aldi, so on and so forth, have pledged they won't sell it. And not only that, but salmon growers have said they have no intention to grow it. They say that because of consumer opposition, but also because the product itself has failed to really live up to the benefits that it purports. So there really isn't much of a market for this fish, and it appears dead on arrival. So that begs the question, why is FDA spending so much of its precious resources and limited capacity trying to advance this product? The perspective of my organization is that the kind of DC playbook is not from consumer advocacy groups as much as it is from the biotechnology industry. We looked at lobby records from the Center for Responsive Politics and found that the food and ag biotech companies, so not pharma, but just food and ag companies, spent more than $500 million over a decade-long period lobbying Congress and donating campaign contributions. I think we can all agree that it would be naive to assume that that this financial largesse has no impact. And for GMO salmon, the impact is a very favorable industry-friendly regulation called the New Animal Drug Application, which we just heard about. You know, there is a certain perspective that there's a logic and rationale to it, but from my perspective, the rationale was that it was a favor to industry, and it's a very weak process that inadequately assesses the risk of this product. So let's talk about the New Animal Drug Application. What you haven't heard is that FDA does no independent science. So yes, they are reviewing science. Yes, there are hundreds of pages of science and data, but it all comes from the product behind this fish, Aqua Bounty Salmon. I think you can all understand from a common sense perspective, but I'll just lay it out. There's an inherent conflict of interest. When all the data and science that exists on a product comes from a company that has a financial interest in that product, in presenting the science in a favorable light. And among other weaknesses, we often see the FDA confusing the absence of evidence with the evidence of absence. That means the FDA will say, well, we don't have scientific data to show that it's safe or unsafe. So because and from that they conclude that there's evidence of an absence of safety problem. It's a very weak standard. So I'll move into environmental safety issues. The FDA is not the only federal agency that has regulatory jurisdiction over this fish. There's also the U.S. Fish and Wildlife Service. And when FDA in 2010 came out sort of guns blazing to approve this fish, Food and Water Watch, my organization, wondered what Fish and Wildlife Service had to say about FDA's review. We filed a Freedom of Information Act request and got internal documents and memorandum in which their senior scientists almost universally were very critical of FDA's environmental safety work. To a certain extent, that stands to reason. The Food and Drug Administration doesn't have an enormous institutional history or capacity looking at aquatic environments, aquaculture. So I think it was odd to Fish and Wildlife Service and odd to a lot of outside observers of why the FDA, in a largely unilateral fashion, would try and assert the environmental safety of this fish. But one telling comment from a PhD scientist was maybe the FDA, should watch Jurassic Park. Has everyone seen Jurassic Park here? If you haven't, it's a great movie. Read the book also. There's a brilliant scientist, John Hammond, who decides that he's going to resurrect or de-extinct the dinosaur colony. And the way he's going to do this is any potential problems, he's so smart that he can out-engineer them. So he comes up with 3 levels of containment. You have biological containment. They're all going to be female dinosaurs, so they can't reproduce. There's going to be geographic containment. They're going to be on a remote island away from other species and plants, so there'll be no interaction. And then there'll be physical containment. You remember the gates that are up to enclose the dinosaurs in the park. I guess I don't have to say how that story ended. That's science fiction, obviously, but the best fiction speaks to reality, and it certainly does in this case. So the containment plan actually has 3 containment methods, not 2. The first is biological containment. As you heard, the sterility process that Aqua Bounty is using is not 100% effective. FDA's own assessment says that up to 5% of GMO salmon will be fertile. That's not an insignificant number, especially if you imagine that Aqua Bounty really, this product takes off and you have billions of salmon all around the world in production. 5% is not an insignificant number. The fish are all female, that is true. What about geographic containment? These are supposed to be grown in inland facilities away from bodies of water that could support the fish. But I think a more apt terminology would be to say that they're grown on water facilities. So they have 2 facilities, as Dr. Blum noted, one in Canada and one in Panama, both of which the surrounding watersheds have suitable temperatures to support escaped salmon. This is from the FDA environmental assessment talking about the Canadian facility. It says for most of the year, the temperatures in the water adjacent to the facility are suitable for salmon survival. Elsewhere in the FDA's work, they talk about in Panama how they're suitable all year round. And then finally, physical containment. These are grown in inland facilities, and they're supposed to have multiple layers of redundancies, of containments, of filters and walls to keep any fish from possibly escaping. If it gets through one, it should get caught through the other. If it gets through the other, it should get caught through a final fail-safe. But here, this is a press release from 2008 that Aqua Bounty issued to investors, alerting them that the damage by an unusually severe storm caused the water inlet system for tanks to fail during the night, with the result that all of these fish were lost. I just think that a reasonable approach to this is to think about, accidents are going to happen, whether it's a management problem, whether it's a natural disaster, whether it's theft in a black market that arises around this fish. Accidents are going to happen. And I think the prudent, measured risk assessment paradigm is to consider, okay, these fish are going to escape, and when they do escape, what's the environmental impact going to be? The FDA heretofore is largely focused on, well, we don't think the fish are going to escape, so we don't really need to thoroughly assess what the risks will be if and when they do. Just real quickly, The Guardian, also the newspaper in the UK, they wrote about how officials in Panama fined Aqua Bounty's operations the maximum allowable amount, $9,500, because of failures to secure permits and regulations, some related to environmental safety. So we've seen in a relatively short tenure of commercial business, this company has had a really atrocious track record of management. I think it's clear to say that accidents will continue to happen. This is the blown up picture that Dr. Blum already showed you. This is Aqua Bounty's quote unquote Fort Knox. When the Guardian newspaper went down there for a visit, they described it as a fading and run down shed in the middle of the Panamanian forest. Doesn't exactly instill confidence for the world's first ever biotech food animal, which in my mind I'm thinking glass, steel structures. And so finally, on a final note on the environmental risk, once a fish escapes, there's no way to retrieve it. It's like an insect. Once it escapes, you can't get it back. So I think it's really important to have a robust and comprehensive view of what the risks of this fish are. I'll move into animal safety and food safety risks with just a brief mention. We've already heard this in some of the previous panelists, but there are unintended consequences to genetic engineering. It's a method of breeding that combines genes in a way that would never happen in nature. So GMO salmon is only as closely related to one of its gene donors, that's the ocean pout, as a human being is to a dolphin. And we know that when you combine genes in this way through transgenesis or genetic engineering, you're not going to get one and only effect. Aqua Bounty hopes that this gene construct will impart a faster growth rate, but is that the only thing that it's going to do? Might it also have effects on the safety of the animal? Might it also have effects on food safety? So on food safety, I'll run through these very briefly. Again, I think the big thing to keep in mind is that all of the data we have on food safety comes from the company, Aqua Bounty Technologies. And in my mind, and I think in a lot of consumers' mind, and I think in a lot of scientists' mind, that's not really a robust body of independent literature on which to base a precedential regulatory decision. So you did see many statistically significant differences in nutrition. There's a question, as it was explained earlier, this is a growth hormone gene construct that's in the fish. Well, what does adding a growth gene hormone construct do to the growth hormone of the fish? That's a good question to ask. That's a question that was asked. Aqua Bounty collected the data, and they didn't find any growth hormone in any fish they examined. One independent scientist looked at it and said, it must be imprecise instrumentation. It's like a cop setting up a speed trap using a radar that can't detect speeds under 120 miles an hour. Obviously, with an imprecise instrument, you can't do the job. On allergies, very briefly, FDA only looked at 6 fish. No statistician would say that's a sufficient number, and in fact, several statisticians have come out and said that's an insufficient sample size to draw food safety conclusions about allergies. Interestingly, they did find a statistically significant difference that FDA still chose to ignore. Finally, on animal safety, as part of the new animal drug application, the FDA should show that this drug or this gene construct is safe for the animal. And all the evidence indicates that that's not the case. Scientists have been using similar growth hormone gene constructs for many years to try and experimentally to try and modify fish. And in many cases, they find that fish end up having health problems, premature mortality, abnormalities, and you see some of that with aqua bounty salmon also. So in Canada, like in the United States, there is an ongoing debate about this fish, and we got a copy of a draft review from the Department of Fisheries and Ocean Canada, and they determined that there's a reasonable certainty that AAS, that's aqua advantage salmon or GMO salmon, is more susceptible to this bacteria than domesticated comparators. This bacteria is important because it leads to furunculosis, a very commercially important disease in aquaculture. If your fish has a lowered immunity, if your fish is more susceptible to disease, that raises not only animal welfare issues, but also commercially relevant questions about how well this product will do in a commercial setting. Among other determinations from the Department of Fisheries and Ocean was that the study design was too restrictive in scope to provide a satisfactory answer to the question of whether the overall health of GMO salmon may be compromised in a commercial setting. So finally, on growth rates, we've heard a few times that this fish really does what it says it can do. It can grow twice as fast as normal fish. It can reach market weight in half the time as normal fish. That's actually not true. Or if it is true, it's not supported by independent science. As a matter of fact, the benefit claim that the company submitted to the FDA, this is the official benefit claim that will be on the product or the package, is far more modest. It's not that the fish grows twice as fast as normal fish to market weight. It's that up to a size of 100 grams, it can grow at an unspecified faster rate. So normally you would harvest a salmon at about 4,000 grams. So we don't know anything about how fast GMO salmon grow to 4,000 grams. We know that it grows faster than at an unspecified rate up to 100 grams, but that really doesn't tell us very much about the growth rates of this fish, about the commercial potential of this fish. And there hasn't been independent science looking at this issue. There's been some peer-reviewed science published, paid for by Aqua Bounty, authored by Aqua Bounty, but not independent literature attesting to this fact. And not only that, but you have the independent salmon industry who's up in arms. And remember, I told you that they're very much opposed to this fish, and it's not only because consumers don't want to eat it, it's also because they say it confers no benefit to commercial aquaculture. As we learned for decades, scientists have been using selective breeding, traditional breeding methods to coax a number of commercially important characteristics out of salmon. That includes growth rate. So here you have a salmon grower, and he uses the term that Aqua Bounty salmon is a solution in search of a problem. I don't know if you can read it, but the dotted line is Aqua Bounty salmon, and the colored lines are traditional salmon, non-GMO salmon, and you see them growing as fast or faster than genetically engineered salmon. You certainly don't see anything like a doubling of growth rate. So it's really a bombastic, exaggerated claim that is very widely cited in the media especially, and it's really distorted the public discourse and also the scientific discourse on this topic. So I don't know how I'm doing on time, but as we all know, the FDA approved GMO salmon as safe to eat and said it needs no label. Yet GMO salmon has not yet been approved as safe to produce in the United States. So again, if you remember the concerns that the U.S. Fish and Wildlife Service has had, they also have regulatory jurisdiction over Aqua Bounty's operations. FDA, their approval of safety basically means that it's okay to produce it in Panama, a country that arguably has the least regulatory capacity to manage the risk of this fish. But in order for Aqua Bounty to start production anywhere in the United States, they have to get a sign-off from the Fish and Wildlife Service, which, as I've noted earlier, has had very significant concerns with the level of environmental science that FDA has done. The U.S. Fish and Wildlife Service has strongly recommended an environmental impact statement for all grow-out facilities located in the United States. That was in a memorandum transmitted to the Office of Management and Budget. And so an environmental assessment is a years-long, very robust, very detailed environmental assessment that differs markedly from what the FDA did. The FDA used a program called the environmental assessment. Sorry, this is confusing, but environmental assessment and environmental impact statement. A lot of independent scientists and groups like Food and Water Watch have long called on the FDA to do an environmental impact statement. They sat on their hands for years before they approved this product. They had time to do it. They should have done it, and it sounds like, we can't read the tea leaves, but from everything we know about Fish and Wildlife Service, if Aqua Bounty ever wants to begin production in the United States, they're going to have to do that. So, yeah, we've kind of heard some of this already. So yeah, just to wrap up, to leave time for questions, in Washington, D.C., you often hear agencies like the FDA talk about science-based rules and regulations, but I think it's important to keep in mind that often that the science is highly politicized, and it's developed via intense biotech industry lobbying, and its approvals are based on biased industry science. So, an organization like Food and Water Watch is all for a science-based process, but it has to be good science, it has to be independent science, it has to be robust science. I also did not thank Tulane for inviting me, but I really want to. This is a phenomenal conference, and I'm really happy to be part of it. Thank you.